express K for the following reaction. Okay, the reaction is 8 Na solid plus 8 water goes to 8 NaOH plus 4 H2. Okay, do you include solid or liquid? Oh, that's okay. The poll was, what kind of phone do you use? It was like majority of the class was Apple. Yeah, Apple is common. So it's because they started out, well, I guess it was just like, it's just so common, everyone uses it. And then Samsung came on. Some people like Android, but I really don't know a lot of people who like it. I do know some though. Okay, so let's go back over here. The first question for our review was express K for the following reaction. The reaction is 8 sodium solid plus 8 water and reversible reaction to 8 NaOH aqueous and 4 H2 gas. So we do not include any solids or liquids. So our K is actually going to just be the product side, okay? So it'll be NaOH to the power of 8 over H2 to the power of 4. Agreed? Now, if I have something in the question where I only have stuff in the reactant side and none on the product side, like product side is solid and liquid, it would be 1 over whatever, okay? Like say if we flip-flop this question around and this was the reactant side, the answer would be 1 over NaOH8 for H2 to the power 4. You put the 1 over on the top. Are we clear? So just keep in mind that that sometimes can happen in the question. Usually you do the products over the reactant. Since there's no reactant here, we just leave it like this. Now if you have no product that's aqueous or gas, it's just all solid liquid, you would do 1 over that thing. Okay? So that's the first question. Now the second question here, still pretty simple. It says determine pH of 0.348 molarity barium hydroxide solution at 25 degrees Celsius. So this question here is a strong base, right? But the trick here is there's 2 hydroxide. A lot of people forget to multiply the concentration by 2. So that's a common mistake here. Do not forget that. So hydroxide concentration is actually 2 times 0.348. That's what people always miss. So you have to use 696 instead of 348. If you use 348, the answer will be in your answer choices. So just remember, you gotta watch out for if there's 2 hydroxides in there. So in this case, POH equals to minus log of 0.696, which is 0.16. Therefore, pH is 14 minus 0.16. Okay, so we have 13.84. Everyone good here so far? Okay, so far so good because the questions are randomized here. You will see a variety of questions and they're all randomized, okay? And it's from basically all equilibrium chapters here. So the next question here is going to take a little more work. This one here, let me write it out. A 25 ml sample of 0.150 molarity hydrofluoric acid is titrated with 0.150 molarity in NaOH solution says what is the pH at the equivalence point. KaHF, which is hydrofluoric acid, is 3.5 times 10 to the minus 4. That's given to you. Okay, so just from this statement here, we have a weak acid titrating with a strong base. Your pH or equivalence point, you expect it to be a basic number. The test actually should have 20 questions, I think. It's 20 questions, and I believe there's 2 extra credits, so you can get 110 on the test. But there's 30 on the review. Okay? Because each question will be worth 5 points, and I think I like to put 2 extra credit every time, so you should get 22 questions, but really only 20, and 2 of them are extra credit. It's just extra, so it'll count out of 100 instead of 110. Okay, so let's go back to this question here. The pH is going to be basic pH. Now, why in the world is it basic pH though? So here's the explanation. At equivalence point, you have just the right amount of OH to balance out the H over here. Okay, so basically you have HF plus OH. Okay, and then you will use this HF, the H here will react with the OH here to make water. And then you'll make F negative left over here. Okay, now this part here, we are going to use, see how the molarity is the same, 0.15 and 0.15, right? So that means at equivalence point, I need 25 mils of the base, agree? So the moles is the same. Moles of H and moles of OH will be the same here. So basically, I need to calculate the moles there, okay? How many moles is that? So to find the moles, I will just take this volume in liters times the molarity here. I should be able to get the moles right there. So if you do that, I'm going to do it on the side over here. So 0.0250 liters times 0.150 moles HF over 1 liter. And I get my moles as 3.75 times 10 to the minus 3 moles. Okay, and this is moles of HF, which is the source of H. And then that way I know I'll put the same amount of hydroxide in so I can neutralize it out. Okay, so the idea is if you have HF and OH, H and OH is neutralized out 1 to 1, right? And then you create 1 mole of this. You see what this guy is? This guy is the conjugate base of HF. And that's F here is the reason why the pH equivalence point is slightly basic, because you still have a weakly basic anion floating around in the system at that point. So basically, I know the reason why it's basic is because it's an F ion that causes it to be basic. So in this case here, I'm going to say I have before I'll write it out, but you really, before the addition, and then we add some OH, and then we do the after. So before that, we had 3.75 times 10 to the minus 3 moles, right? And then we know to add exactly 3.75 times 10 to the minus 3 moles of hydroxide. These were 0. So because of that, all of this turned to 0. This one turned to 0, that one turned to 0. And then, but this F here, you have 3.75 times 10 to the minus 3 moles. So this one's still floating around. Okay, this presence of F here is why the pH is basic. So that means F here is a base. So I have to write an equation for it as a base here. F plus water. I can make HF plus OH negative. That means the Kb for this F is HF times OH divided by F negative. And what is this value? Well, we don't know it. We know Ka is this value for HF. So you use the Kw to get it. Okay, so remember Ka times Kb equals to Kw, right? So the Ka for the counterpart is 3.5 10 to the minus 4. Let's put that in here. And then we'll solve for Kb of the F by equating it to 1.0 times 10 to the minus 14 here. Okay, so Kb is 1.0 10 to the minus 14 divided by 3.5 10 to the minus 4, which will give you 2.86 or 2.9 10 to the minus 11. Okay, I'm going to go ahead and write it down here. 10 to the minus 11. So you take this here, that's all you need. Like, this is the problem. This is how you get the pH here. Now remember, because this is base, when you get your X, it's high POH, and then you have to get your pH after that, subtracting from 14. So let's go ahead and set our ice table up. We have F, ion, I have HF, and then I have hydroxide. I have ICE. So in the beginning, I know the moles of my F here, but I need to put molarity in there. So how can I get the molarity? I take the moles divided by the total volume. Now I do know it was 25 mils over here, right? So 25 and 25 will be 50. My total volume is 50 mils. So I'm gonna go ahead and write the calculation for molarity of F negative here is 3.75 times 10 to the minus 3 moles divided by 0.05. And then I will get 0.075 molarity F negative. Okay, that goes in my ice table. So that was the base that was still hanging around. And then 0, 0, because there's none of this in the beginning. Okay, so this is plus x minus x. And then we'll write it in terms of x. So let's put this in here in terms of the Kb formula. And write it over here. So HFOH is x times x divided by 0.075 minus x. That equals to 2.86 times 10 to the minus 11. So because this K is so small and compared to that, I'm going to go ahead and assume this one is insignificant, this x here. Okay, so x squared would be 2.86 times 10 to the minus 11 divided by 0.075. And then you take a square root of that, you can get the x answer. X equals to square root of that, which is 1.46 times 10 to the minus 6 here. So you can check it, but visually you can tell at 10 to the minus 6 and 10 to the minus 2 times 100, it's going to be less than 5%. Okay, but if you forgot, I'll write it out for you. Check step is 1.46 times 10 to the minus 6 divided by 0.075. And then you times 100 to get the percentage, and you want it to be less than 5%. In the case, yes, it is less than 1.9, 10 to the minus 3%. So it's okay to do our shortcut here by saying this x is insignificant. So once you find the x is OH at equilibrium. So POH is minus log of the x value, which is 1.46, 10 to the minus 6, which gives you the POH of 5.83. Okay, to get the pH, then it's 14 minus 5.83. It will be 8.17. And that's why we say the pH at the equivalence point is slightly basic. It's really because the presence of the anion that comes out is weakly basic, and you do a base problem from the anion. Okay? Hold on a second. 10 to the minus 5. You mean for this one here? Let me double check. 1.46, 10 to the minus 6 divided by 0.075 times 100. Oh, it times 100. And then you get 10 to the, for the first one.
I get that for the 2.86 times 10 to the negative 11 divided by 0.075. And then I do the square root. I don't get the 1.46 times 10 to the negative 6.
So how did you do it? So let me show you how I would do it, okay? So I would take this 2.86. Oh, you can't see, I'm gonna lift it up. 10 to the minus 11, right? And then I want to divide by 0.075, which is that number right there, okay? So I get that, right? And then you take a square root of it, because this x squared here. Oh, wait, I got 1.952. Never mind. Did I write something wrong in here?
You multiply, not divided.
I multiplied it. Wait, hold on a second. Where?
Like you divided it instead of.
There we go. That would solve all our problems.
Okay, yeah, I see.
Yeah, because it was divided over here. So 2.86, 10 to the minus 11 times 0.075. There we go. Now we get that. And then you square root of it. All right. Thank you. So we got this part. So the answer over here is x over here is still fine. And then know that the x is OH here. So we have a titration here, okay? It says 25 ml sample of 0.150 hydrocyanic acid is titrated with 0.150 molarity NaOH. What is the pH after 26 mils of base is added. Ka of the acid is 4.9 times 10 to the minus 10. So whenever we look at titration, there's different points. This one here, the molarity of acid and a base is the same, but this is a weak acid and that's a strong base. So to get to equivalence point, I would need 25 mils of 0.150 molarity NaOH. That point I know is going to be a slightly basic pH, and because it's strong base and weak acid. Now I know I need 25 mils to get to that point. If I put 26 mils, I essentially have more hydroxide floating around now, because at equivalence point, the hydroxide and hydronium ion are 1-to-1, and then that's what equivalence point means. So when you have 26 mils, we have some excess of hydroxide. So what you do is you find how much excess of hydroxide we have. And then we'll find POH from the molarity, and then we'll find pH. So that's the idea, all right? So to find how much excess, I need to know that the total volume, because I need molarity, the total volume is 26 and 25 here, so I know total volume is 51. Okay, and let's go ahead and find the moles, that way I can find molarity. So moles is 26 minus 26 is excess, because I know I needed 25. So 26 minus 25, I essentially have 1 mil of excess, correct? So 25 mils is 1-to-1 H2OH. So 26 mils has 1 mil excess OH, okay? So that 1 mil here, well, let's calculate 1 mil of the excess, and the molarity was 0.150. So let's go ahead and turn into liter first. 0.150 moles per 1 liter of OH. Okay, the molarity of sodium hydroxide is the molarity of hydroxide ion, because it's 1 sodium, 1 hydroxide. So you do this here, you can get the moles. Now that's our moles. To get POH, I need molarity of OH. So I'm going to go ahead and take that moles and divide by the volume in liters. So the volume in liters, let's go ahead and turn that to liters. You divide by 1,000, you get 0.0510 liters. Okay, so to get molarity of OH is 1.50 10 to the minus 4 moles divided by 0.0510 liters. That will give me molarity of around 2.94, 10 to the minus 3. Okay, now with that here, I can go ahead and do minus log of 2.94, 10 to the minus 3 to give me POH, okay? POH here is going to be 2.53. Now, when you do this question here, if you see 2.53 showing up on the ABCD choice, don't pick that, because why? They asked for pH, right? They didn't ask for POH, so this method only works if molarities are the same. Yes, if molarities are the same, you can just do the volume and kind of figure it out. But if the molarities are different, then you want to go ahead and calculate the moles, like say how many moles this is, how many moles that is, and then take the moles of the base, which is going to be bigger, minus the moles of the acid, because it's moles of OH minus moles of H+. Because the molarity here is the same, we can just take the volume and then calculate the moles there. okay? So if the molarities are different, let me see if there's one that's different. No, so far it's all the same here. I think you had different ones in your homework, right? So yeah, we're about to see one where it's a little different, but you'll notice that the questions I put on the test, I try to not put ones that have like super, super long math. So a lot of times they are the same. But remember, if they are not the same, you will have to calculate the moles of the sodium hydroxide minus the mole of the acid to get this number here. Okay? All right. Now, once you get POH here, we can get pH as 14 minus 2.53, which is 11.47. Okay? Let's go into the next question. I'm going to write it out, and let me know if you guys have questions, okay? So here's a reaction. Kc is 1.10. And if you notice, there's a lot of solids in here, which we don't count solids, okay? I'm gonna move my computer a little bit. Oops, hold on a second. All right, so it says here, a reaction mixture contains 0.20 molarity CH4, 0.69 molarity CO2, and 1.5 molarity H2O. Now, so this question actually asks us which following statement is true. So I'm going to write down what the statements are, okay? So which of these statements are true? A, shift right. Or shift to reactants, that's shift left, I lied. Reactants is on the left. B, equilibrium constant increase, will increase. C, reaction quotient will increase. And D, reaction shift to product side. E, system at equilibrium. So basically they're asking you what's going to happen here. So these are all different scenarios. You just have to find which one is true. They gave you these concentrations here. They didn't say if it was at equilibrium concentration or not, so you just assume it's not. So that means it will be a Q that you're calculating. And then they gave you the K. If you calculate the Q and compare the K, you can tell if it's going to shift to the reactant side or the product side. And then, well, obviously it's going to be one of these answers. If this is not it, it must be this one. So these answers here, well, it depends. Actually, you can actually eliminate it, but I'm just going to show you how to calculate the Q, okay? So Q here, the formula is just like the K, so I don't put the solid, but I put the gas in. So I have CO2 to the power 1, H2O to the power of 2, because this H2O is in gas form, okay? And then divided by CH4. So let's put those numbers in. It's 0.69 and then 1.5 squared and then 0.2. So I'm going to get a number, and that number is 7.8. Now 7.8 is bigger than 1.1. Q is bigger than K, so 7.8 bigger than 1.1, right? So if it's bigger than K, you have a lot more of stuff on the top here, which is the products, too much products. So it will shift to the reactant side, shift to the left to the reactant side here. Okay, now equilibrium constant will not increase because they did not mention any change in temperatures. The only time K changes is when you have temperature. Reaction quotient, it can't increase because it's actually too big. It should decrease to go down to K, so that's wrong too, and it doesn't shift to the product side. And it's definitely not at equilibrium. Okay, so when you see a question like this, you just put in those values and basically calculate what the Q is and see if the Q compare it to K and see what happens. Okay? All right, the next question is give the expression for the solubility product constant for PbCl2. So how do you do that? So they're saying expression for solubility product constant. So that means it's Ksp of PbCl2. So PbCl2 is a solid because it's a product, solubility product, right? So your equation was PbCl2 solid, and then it turns to ions. Pb2 plus 2Cl negative Aq. So basically our Ksp is Pb times Cl squared because you have nothing over here on our reactant side. So it's Pb2 plus Cl negative squared. Okay? All right. We'll be writing on reaction ourselves. For this question, all you are given is the first sentence. So yes, you will have to write the reaction yourself. And that's actually probably the biggest hurdle because sometimes you see, well, PbCl2, but I don't know what to write. I don't know what reaction you're talking about. So you have to read from the hints of the question. It says solubility product constant. So that tells you they want a Ksp for PbCl2. Now, if they're asking for PbCl2 Ksp, this guy doesn't dissolve, but very, very rarely. So it's going to be the solid breaking down into ions. Okay. Sometimes another version of this is they'll ask you, give the expression for the formation equilibrium constant, the Kf. And then they'll give you a complex ion, right? So maybe we can do one on the side here. So I'm just gonna show you another example for this, okay? So like they say, give Kf for, what was one of those that we learned? It was COCl for 2 negative, right? So that was the one that we did last. So here's just another question, like a different version of the question that we just had. So Kf for this guy, then you'll just say, well, I need to know that if they ask for Kf, this is a complex ion, okay? So to make the complex ion, it will be my product. And then it comes from these ions here. I know I have cobalt 2 plus, and then I have 4 chloride ion. Okay, so based on this equation here, so they'll only give you this statement. You will need to know how to write the equation and then decide which one is the Kf, okay? So for me here, the Kf would be COCl4, 2 negative, over CO2 plus, over Cl negative. to the power 4. So you see how the Kf looks busier, and the Ksp is only there's ions on the top. Okay, so complex ions and so. It might be some that you haven't seen, but if they tell you like Kf, and they give you these, and they'll give you multiple choice options, you'll be able to figure out, even if you didn't know cobalt was 2+, you should know Cl is -1, and you should be able to distinguish that. And from the answer choices that's given, you can find the hints if you don't know the ions. Okay, but sometimes it does generate different questions, so you might see ones that you haven't seen, but it's just a matter of knowing like ions, and that's like some stuff you learn from Chem 1 too. Okay, now so when they say Kf for a complex ion usually is like a bunch like metal and some ions here. Sometimes it could be water, sometimes it's ammonia, right? And then it has a charge up there. It's a weird looking charge. So that goes up here. And then over here, this one here is always just a solid. And you take the solid and you break it apart. Okay? So you need to be familiar. Like if I give you PbCl2, you need to know, well, this one has 1 Pb and 2 Cl ions. All right. So let's move on to the next question. We'll do number 7 here. Here's another titration, but like read this carefully and see if you can just tell me what point of the titration this is, okay? A 850 ml sample of 0.20 molarity HF is titrated with 0.10 molarity LiOH. Determine pH of solution after the addition of 850 mL of LiOH. The Ka of HF is 3.5 times 10 to the minus 4. So here's another titration question, all right? Now with this titration question, always take a look. I have acid and I have base. This is a strong base, and because it's group 1 hydroxide. This is a weak acid because they gave me the Ka. So it's weak and strong. If it were at equivalent point, that means the pH is going to be a little basic, okay? But take a look here. You have 850 mils of 0.2, but you're using 0.1 molarity of LiOH, right? So in this case here, you can calculate the moles because you see how they're different molarity here. So I can show you how we calculate the moles here. Okay, so you see which part of titration it is by saying, okay, let's take the moles of this acid here, and then I'll calculate with this amount of base and see, you know, who I have excess of or what point of titration I am. So I'm going to go ahead and start with the moles of H+, okay? So that way I can say, well, I have 850 mils, and 1 liter is 1,000 mils. And then the molarity of the HF was 0.2, so molarity of H+ is also 0.2 moles per liter, so I can get my moles here. Now this gives me 850 times 0.2 divided by 1,000, 0.17 moles of H+. And then I can do moles of OH here from the lithium hydroxide. The lithium hydroxide, the molarity is actually half of it, right? So I'm going to go ahead and put that in. .1 here and 1 liter. So this molarity, obviously the moles here will be half of this. So you actually calculate 0.085 moles. Okay, so it is not equivalence point, it's before equivalence point. Agree? Because if it was equivalence, you would have needed double of 850 because the molarity was half. But you can see here it's not 0.17 moles of hydroxide, but it's exactly half of it. Now, do you remember what's the half equivalence point meaning? So this is actually the half equivalence point right here, because you needed double of 850 if you wanted to get to equivalence point. Because it's half equivalence point, you don't have to do this whole titration thing. If you remember, at half equivalence point, pH of your system equals to the pKa of the acid. Do you guys remember that? Now, I did work this out in class one time, and I actually showed you the whole calculation part. But when you're in a test, if you know it's pH equals pKa, don't bother doing the whole ice table because it takes so much time. Okay, so I will show you the ice table reference question. Let me flip back to the page in a second, but let's go ahead and calculate what the pKa here. They gave you the Ka, right? So if you wanted to find the pKa, it's minus log of 3.5 times 10 to the minus 4. That should give you your pH, okay? And the answer here is 3.46. So if you were used to doing these problems here, a lot of times you don't even have to calculate this. You can take a look and say, well, A50 of 0.2 and A50 of 0.1, this is halfway to the equivalence point, pH equals pKa, and you can just go straight through this calculation. But if you weren't sure, you're not familiar, or maybe the numbers are weirder than this, just go ahead and calculate it. And if you see halfway to equivalence point, you can just go straight to the pH equals to pKa. Okay, now let me show you the question that we did in class. That was a long time ago. Right here, it was this question here. It says 0.1 acid, 0.2 KOH, and then pH at half equivalence point. So they asked you to get to equivalence point, you actually need 20 mils of KOH. We calculate that. Right here from the moles. And then half equivalence point will be 10 mils, agree? So the question with 10 mils here was right there. And once you get the moles, you have to set up this little table here. And if you see it's halfway to equivalence point, because this is acid and halfway is the base, you see that the base and the acid ratio is 1 to 1. It's the exact same number, and that's why pH equals to pKa at that point. So you can save a lot of time if you remember it, but this is how we would have done it. Okay? So that was from, I don't know how long ago, but it was from this question, okay? When we were doing titrations. All right, so if there's no questions, I'm gonna keep going to the next question. I'll leave this over here. All right, question number 8 for you guys. Remember, our test is going to be 20 questions plus 2 bonus, so 22 questions altogether. It will be jumbled up and it'll be very similar to our practice test, okay? Which of the following compounds will have the highest molar solubility in pure water? So molar solubility is S, okay? So the first one here is FeS. Ksp is 3.72 times 10 to the minus 19. B, MgCO3, Ksp is 6.82 times 10 to the minus 6. C, PbSO4, Ksp is 1.82 times 10 to the minus 8. D, COS, Ksp is 5.00 times 10 to the minus 22. Now, the first thing you want to do is, if they ask you for molar solubility and they give you the Ksp, you have to check, are these guys all the same number of ions? This is Fe and S, so 2 ions, Mg and carbonate, 2 ions, Pb and sulfate, 2 ions, cobalt and sulfide, 2 ions. So these are all 2 ions. So when they're all 2 ions, I don't have to calculate the S. If they're different ions, I have to calculate the S before I can compare them. Okay? So when the samples, or when the answer choices, when the compounds have same number of ions, basically the Van Hoff factor, how many times do they split? They both split 2 ways, then good, you can compare it to Ksp. We can compare Ksp. No need to calculate S to compare. Now, if your ions are not 2, 2, 2, 2, 2, or 3, 3, 3, 3, 3, all of them, if there's one of them is 2, one of them is 4, one of them is 3, then you want to take the Ksp and calculate the S. Okay, now to do the Ksp, calculate the S, you will have to use the ICE table like we just did in class. And the example will be like this. Okay, so it will basically, here's the Ksp, and then you do this, find the S that way. Once you find the S, and then you compare the S. Okay, but in this case, we don't have 2 since they are all 2 ions. So that's nice. Now, if they're not, then you go ahead and calculate the S. So if they want the highest solubility, that means I'm looking for the biggest Ksp because the biggest Ksp has the most ions. That way it should be the most soluble, higher solubility, okay? So that should be B here. Now, if they change the question and just say lowest molar solubility, you would pick the smallest one. And which one would that answer be? It would be D. Okay, so it just, you know, there's different ways they can ask. Sometimes they ask for the highest, sometimes they ask for the lowest. Just make sure you know what you're looking for. And especially if they have the same number of ions, we can compare just the Ksp. And now if they come up with different ions, you have to calculate the S. And then once you get the S, you pick the biggest S for this one. And if they want the lowest molar solubility, pick the lowest S. Okay?
Could you show an example of like when they would
Sorry,
be
did you
like
have a question?
yeah, so could you like show an example of when it would be like when you have different, it splits in different ions and so you have to calculate it?
Let me look for a question that has that. Trying to see. All right, let's do the ones from the notes, okay? So I'm just gonna pull some values up because I don't actually have a question, but I'm gonna pull it up from the tables and we'll just work something from there. So like, I have a table over here. I'm gonna pull some numbers up. So let's write down, let's pick one. So we have, these are all 2. Let's do one that's 3 ions. How's that? We'll do FeOH2, okay? And the Ksp for that one will be 4.87 times 10 to the minus 17. Let's do another one with 4 ions. This one has 3. 1, 2, 3, right? Let's find one with 4. Do I have one with 4 here? No, they don't have one with 4. Well, my table doesn't give me one with 4. So this one has 3. Yeah, I don't have the chart for the 4. I have to look at my big table, but let's just do the 3 one here, okay? So this one has 3. Let's throw this one in the mix. How's that? So we'll add this as choice E. And then so how this one is different from all these guys. So we'll calculate this guy. So in this case here, you would have to calculate the S for all of these, okay? So, but one thing I can tell you though, because of these four are all 2, 2, 2, 2, 2, I only have to calculate the S for this one that has the biggest one, and then compare it to the E and see if this guy is bigger than that, okay? So let's do S for MgCO3. Do we agree? Because I just determined out of these four, this one is the biggest, right? I'm going to calculate the S for this, and I'm going to calculate the S for this, and then we'll compare those two. All right? So let's do this guy right now. So MgCO3. So I have to write the equation. That's solid. It breaks apart to Mg2 plus and CO3 2 minus. Okay? And then, so my ice table is Mg2 plus, CO3 2 negative. Sorry, I'm gonna put the 2 negative on the inside. Can you guys see okay? Do you want me to zoom in a little bit? 2 negative. Okay, so if it's in pure water, it's 0, 0 here, and it will be plus S, so it's S and S. So that means Ksp is S squared. Agree? So if I know what the Ksp is, Ksp for this guy is, it was 6.82. So 6.82 times 10 to the minus 6 equals S squared. That means I just square root this number, I can get what S is, okay? Square root both sides. Let's do that. .61 times 10 to the minus 3. Okay, so that's my S for this one. And I determine, based on the Ksp for these four options here, my S for MgCO3 will be the biggest, so I don't have to do these other guys for now. Okay, so I'm just going to do S here, and then let's do the S for this guy. So this one here has 3 ions. When it's 3 ions, the formula is not S squared anymore, it's different. So let's write it out. The equation is FeOH2. Okay, and then we'll split it to Fe2 plus 2OH negative. Okay, how I know this is 2 plus? Because I know hydroxide is -1. So those are the things that you have to remember, like simple charges. A lot of times, if you don't know the charges for the KF question, you'll see the hints in the answer choices. So like those, you'll see that, you'll see that Cl will be -1, CO is 2 plus. You'll see those values in there. But hydroxide here is -1, Fe2 plus, and then our ice table is Fe2 plus, and then hydroxide, and then ICE. I is initial 0 because it's in water, and this one here is plus S. This one here is plus 2S. So this is S and 2S. And then when you do Ksp, because this Ksp was Mg2 plus times CO3 2 negative, right? This one here is Fe2 plus times OH negative, but you got to square that guy. So it's a little bit different. So this one is S, and then 2S, but squared S. So it's actually 4S cubed. So you see how this Ksp is S squared, this one is Ksp is 4S cubed, so it's a little different, right? So let's put in here 4.87 times 10 to the minus 17 equals to 4S cubed. You divide it by 4 and take it to the root of 3, cube root, okay? So I'll write it out as 4.87, 10 to the minus 17, divided by 4, and then you take a cube root of everybody. So let me do that one. So I got 2.3 10 to the minus 6. So in this case here, I actually am still going to be picking magnesium here because they asked for the highest molar solubility, the biggest one. So the S for this guy is still the answer. Okay. Do you guys know how to do cube root on your calculator? Please make sure you can find the option there. It should be some function like that. Mine actually has a cube root, but you should be able to find something with the X and you put the value in there. Okay. Now, if they were to ask for the lowest molar solubility, what I would have done was compare this guy's S to well, highest, and then we'll pick the lowest one here. The lowest one in this list would have been this guy. So I would have compared those just to see which one's bigger. Now, in this case here, so that's how I would do it. But I'm just saying, like, and I just wanted to see, show you the difference between if you had 3 ions and this one's 2 ions. Okay. I don't have a 4 ion, so I guess we don't have 4 ions in this list here. Everyone good so far? Let's go to the next question here. Question 9. Okay. Okay. Here's another titration, but a different scenario, okay? 25 mils. Sample. 0.150 molarity formic acid. Formic acid is HCOOH, but even if you didn't know the formula, it doesn't matter. You can just write a generic acid equation, okay? Is titrated with 0.150 molarity NaOH. Same molarity here again, so that's nice. What is the pH? pH before any base is added. Ka of formic acid is 1.8 times 10 to the minus 4. So before any base is added, is literally just what's the pH of the weak acid. There's no titration happening here. You're literally just calculating the pH of the acid, which is a weak acid. Okay, so if you want to do that, so if it hasn't you put any base in, all you have is just the acid, it becomes just a weak acid problem. So we'll write the formic acid. Now, if you didn't know it was this formula, you can easily write just HA, okay? So let's say if you didn't know this formula, let's write generic acid, right? Plus water. And then, so we'll call this A as part of the formula. We don't know the formula. And then you have A minus, and then you have hydronium. Okay, so that's how you would write the equation, right, for any acid. So it doesn't matter if they change the acid on you and you get scared of it. Don't worry, just write a generic acid if you don't remember, if you don't know the formula. A lot of times they'll put the formula next to it for you. But if they don't, that's okay. Just write a generic equation that still work. So in this case here, we want to find a pH before any base is added. So just basically find a pH of this, pH of 25 mils of 0.150 molarity for formic acid, right? So what we want to do is go ahead, write the equation, and then we'll write what Ka is for this acid, which is A minus over H3O plus over HA And that equals to 1.8 times 10 to the minus 4. And then we set our ice table. So, well, if it's just one thing here, all I put is the molarity of that in here. Before any acid is added, the molarity is still 0.1 because it's 25 mils total still. So 0.150, it goes here. None of that, none of that. So it will be plus x, minus x. So 0.150 minus x, x, and x. And then this is pretty small. It's kind of close to 10,000. So we'll go ahead and do it and then check it, okay? I'm gonna go ahead and put the Ka values in here. So Ka is x times x divided by 0.150 minus x. And then that equals to 1.8 times 10 to the minus 4. I'm gonna go ahead and take the shortcut here, cross this guy out, okay? And then I have x squared equals to 1.8 times 10 to the minus 4 times 0.150. And then take a square root of that answer, you should get x. So that one equals to 2.7 times 10 to the minus 5, and then square root of that is 5.196. So it's really 5.2 times 10 to the minus 3 molarity. And then we do a quick check. 5.196 10 to the minus 3 divided by 0.150 times 100. You get pretty close to 5%, but it's still under, so we're good. Okay, so now that I know what my x is H, right? So that will give me the pH. So pH is minus log of H at equilibrium, which is x. So minus log of 5.196, 5.2 10 to the minus 3, you get 2.28. So that's the pH of just the acid. Okay? All right, I'm gonna go to the next question here. Oh, here's one. It just has to compare, so I'll write out a question. It says, which of the following solutions would have the lowest pH? Assume they are all 0.1 molarity in acid at 25 degrees Celsius. And then they gave you the Ka values for all the acids. So here's one. HCN, Ka is 4.9, 10 to the minus 10. HCHO2, Ka is 1.8, 10 to the minus 4. HNO2, Ka is 4.6 times 10 to the minus 4. DHClO2, Ka is 1.1 times 10 to the minus 2. And EHF, Ka is 3.5 times 10 to the minus 4. Okay, so how would you know which one has the lowest pH? So remember, the strongest acid starts at the lowest pH for the titration curves. And the weaker the acid is, it starts off at a higher pH. You guys remember that? I'll show you the picture of it. On slide number 37, see how the strong acid is always the lowest pH where it starts, and then it's higher and higher as the pH, a weaker acid you use. It starts off at higher pH, okay? So basically, if you want the one with the lowest pH, you're looking for the strongest acid. So the strongest acid should have the biggest Ka value, correct? So it should be D here because this one has the biggest Ka value. Now, if they ask for the highest pH, you just pick the opposite. This one will be the highest pH because it's the weakest acid. Everyone good here? So I'll write it down. Lowest pH, strongest acid, which means biggest Ka. Okay? And then if you wanted to do the highest pH, is the weakest acid and the smallest Ka. All right. Here's the next question. Another true or false statement. Well, not really true or false, but I'll give you the scenarios. Give the direction of the reaction if K is a lot bigger than 1. Okay, this is big K here. It says neither direction is favored. B, the forward direction is favored. C, the reverse direction is favored. D, if the temperature is raised, the forward is favored. Forward direction, okay? E, if temperature is raised, the reverse direction is favored. Now, you cannot say D or E because you don't have the endo-exothermic information, right? So you don't know enough to talk about D or E. Endo or exo will tell you which way it goes if you raise the temperature. But if you don't know that, all you know is K is a lot bigger than 1. K a lot bigger than 1 means K is a big, big number. When K is really big, it favors products. Okay? If it favors products, that means it likes to go in a forward direction because going forward is towards the product. So this is going to the right. That's forward direction, okay? And this one's going to the left because it's reverse direction. So K is bigger than 1 means it's forward direction. It has nothing to do with how fast things are going either. Or you can't tell anything about temperature, you can't tell anything about speed. All you can tell is if it's bigger than, a lot bigger than 1, it favors product side, which is the forward direction, okay? Why is a generic acid equation used when no base is added? Okay, I'll show you that. So the question was, why do we use generic acid question when no base is added? Now, if you were doing a titration, this is basically a titration curve, just whatever acid, right? And they say, what is the pH before any base is added? Before any base is added, what's in your flask? The only thing in there is weak acid. So it becomes a problem where, can you tell me what the pH of this weak acid is? That's what you're trying to look for. And that's why I wrote only the acid equation here, because there's no base in there yet. I'm just looking strictly for that acid here. Okay? So it's really not a titration question indirectly because they're asking you before any base is added. It's just basically what's the pH of your acid. Okay, everyone good so far? And then good with this question too, number 11. If that's the case, I'm going to go ahead and do number 12. COCl2, this is gas, breaks to CO gas and Cl2 gas. Okay, and then it says a reaction mixture initially contains 1.6 molarity COCl2. Determine the equilibrium concentration for CO if Kc for this reaction at this temperature is 8.33 times 10 to the minus 4. Calculate this based on the assumption that the answer is negligible compared to 1.6. So they're saying x is really small compared to 1.6. Go ahead and do your shortcut. Okay, so this one here is basically one of the questions from like the first chapter, like chapter, is it 16? Yeah. Where they give you the K, they give you an initial and find one of the equilibrium concentration. You know, we're so used to finding pH, but pH is minus log of one of those things. We're looking for a CO here. So given this equation here, we can write the Kc formula. Kc here is CO Cl2 over COCl2. That equals to 8.33 times 10 to the minus 4. And then we'll go ahead and set at the ice table. So initially you have 1.6 molarity and 0, because they don't mention it. So these guys are going to go up 1x, and that's going to go down 1x. And they said x is negligible compared to 1.6, so you can cross this one out and you don't even have to check it. So put this back up there. Okay, because 1.6 minus x, I crossed it out over there. That equals to 8.33 times 10 to the minus 4. So x squared is these two values multiplied together. Should give you 1.33 10 to the minus 3. Square root of that is 0.0365. And really you only need 2 suffix because we have 1.6 there. So 0.37. Okay. Everyone go with this? So it's really nice when they tell you calculate this based on the assumption that answer is negligible. This statement here, it means that you can cross out your x. Okay? All right. Let's go to the next question. In a reaction mixture containing only reactants. What is the value of Q? So the answer choices were -1, 1, infinity, 0, or cannot be determined. So if it's only reactants, there's nothing on the product side, right? So, and then there's something in the reactant side. So Q would be like products or reactant. So it will be no products, right? On the top, so no products will be 0. And if it only had, if it was the opposite, where this is only products, then you have something up here divided by nothing, then that one would be infinity. So in this case, when it's only reactants, it's D. Only products would be C, okay? Number 14, identify the weakest acid. So in this case here, here's our options: HCl, HF, E, HBr, HI. Not enough information. So this one here is binary acid. Okay, binary acid trends you have to remember. So there's two separate trends: oxy acid and weak binary acid. So once you determine you're only looking at binary acid, you got to remember the trends for it. So I want to show you the page, the notes that we talked about this. Okay, so for the weakest acid, the trends for acid. Right here. Number 1, going down a group is stronger, and then if it's on the same period, as you go more electronegative, the more electronegative one is stronger. But going down is the strongest. In this case, we are going down, right? The question was actually based on this. So which one is the weakest? HF is the weakest. Which one is the strongest? HI is the strongest. Okay. Now, and then in our class, we actually did like different kinds of questions. So make sure you remember to check your notes, okay? And oxy acid had different trends. Oxy acid is looking at most electronegative. The more electronegative the Y is, the stronger. And the more oxygen, the stronger. And we also did some ranking for these guys as well. So just keep in mind, if there's a weak or strong question, sometimes they ask you to rank from weakest to strongest, strongest to weakest. Sometimes it's oxy acid, sometimes it's binary acid. So you just have to make sure you know these trends, okay? So let's go back to the question here. It says, focus. Identify the weakest acid. So that would be HF. The strongest in this list would be HI because it's the lowest in the periodic table. Okay? All right, let's go to the next question. So number 15 here, 1.5 liter buffer. Solution is 0.250 molarity in HF and 0.250 molarity in NaF. That was nice, they gave us a molarity already. It says calculate the pH of the solution after adding 0.0500 moles of NaOH. It's solid NaOH. And it says assume no volume change. That's nice. Upon the addition of base Ka for HF is 3.5 times 10 to the minus 4. So in this case, your buffer is 1-to-1 ratio. That's nice. And then you are going to add some base, strong base in there. Okay. So you want to see here that when you add a strong base in from the sodium hydroxide and you go into a buffer, which part of your buffer will self-sacrifice? If you put a strong base in, the acidic component has to self-sacrifice. So your equation is HF is going to revolve OH, and you're going to make water, and you're going to make some F negative. So that's the idea there. Okay, so before we start, because you need the value of moles here, we need, before we add OH, addition of OH, and after we add it. So we gotta find how many moles of HF and F before we add it. We know the moles is the same though, so I'm just gonna calculate one of them and put the same answers for moles of F and HF, okay? They also said that we added 0.05 moles of sodium hydroxide, so I'm gonna go ahead and put that in there. That's the addition. So let's go ahead and calculate the moles of F and HF. F is from NaF here. HF is from that guy, and the volume is 1.5 times this molarity for this moles, 1.5 times this molarity for F moles. Same answer. So I'm going to have and calculate on the side here. Moles of HF equals moles of F here, same number from these two, okay? Because the molarity is the same. So I'm going to calculate just one. So take 1.5 liter, 1.5 liter times 0.250 moles HF and 1 liter. So I get 0.375 moles. Okay, I'm going to put that here. And this one too, same number, right? Because the molarity is the same. If it was different, just calculate it again. Take the molarity of NaF times the total volume. So you got that. Now, when you add this hydroxide in, all of it gets neutralized because you still have a lot of you have a lot more acid than you do with the incoming base. So what happens to this acid? It goes down by that number, 0.375 minus 0.05. Great. And this one here will go up, 0.375 plus 0.05. Okay, so our answers here are going to be 0.325, and this one is 0.425. Now, once you have the ratio of base and acid, you put it into your formula, pH equals to pKa plus log of base over acid. Now remember, we can straight use the moles in here. You can calculate the molarity by dividing by 1.5, but both of them are dividing by 1.5. The ratio is still the same. So skip that step. You can save some time. Minus log of Ka, 3.5 times 10 to the minus 4, plus log of 0.425 over 0.325. So you have to know which one's base, which one's acid. This is the basic component, that one's the acidic component. We should be able to get our answer. And the answer comes out to 3.57 here. Everyone okay with this part? All right. If there's no questions, I'm going to go to number 16. So here's number 16. They're asking you for the missing K. Okay, I'll write down the steps. A plus 2B, AB2, K is 59, and then line 2, AB2 plus B, AB3. K is question mark. The third line, A plus 3B equals to AB3. K here is 478. So when I have a question like this, we're trying to manipulate lines until we get this part. So, you know, we're going to name this line 1, line 2, and line 3. We're going to use line 1 and line 3 to get to line 2. Okay? So on line 1 and line 3, those are my options to manipulate. I'm trying to get line 2 as my answer. So what's in line 1 that is the only source of the puzzle piece that you can put into line 2 that doesn't repeat in line 3? A can't be used because A appears in line 3 also. B also can't be used because B appears in line 3. I can only use AB2 because AB2 doesn't appear in line 3. AB2 is going to be fitting into line 2, but it's on the opposite side. So that means I have to flip line 1. So when I flip line 1, I get AB2 is A and 2B. And my K here is also flipped, so it's 1 over 59 now. Okay, now let's take a look at line 3. I can't use A, I can't use B, but I can use AB3. AB3 is going to fit exactly in line 2 just the way it is, so keep line 3 the same. So A plus 3B goes to AB3. K here, keeping the same, 478. Now you add them up and you hope you get line 2, okay? So when you add them up, these are my reactants and these are my products. And A can cancel off. See how there's 3B and 2B? So this 2B is gone now, there's only one B left on the left side. So it's AB2 plus B goes to AB3. That's the answer after you add them. And that actually matches line 2. See that? So to get the K for line 2, you multiply these values together. 1 over 59 times 478. And you will get the answer for K for line 2, which is in this case 8.1. So this is basically manipulating K values like in equations. Okay, this is also from chapter 16. So just keep in mind there might be different questions, and you should have seen a lot of these while you were practicing on homework and all that too. Okay, let's go to the next question if you guys don't have any more questions here. Now we are going to run a little bit over, well, maybe more than a little bit, but I will be recording this and I will post them so you can basically, you know, when it's online, just click on the part where you had to go and then continue watching there. Okay? So if you have to go for another class, feel free to go, but make sure to watch the recorded video. All right, let's do numbers question 17. Determine the ammonia concentration of an aqueous ammonia Kb of 1.8 times 10 to the minus 5 solution that has a pH of 11.3. So this one here is a little more thinking involved here. I actually probably need more space than this. So I might start my work on the next page. So we're looking for ammonia concentration and the solution has a pH of 11.3. From the pH, I should be able to get the POH. And the POH here should give me the concentration of hydroxide at equilibrium, which is good because ammonia is a weak base here. It means when you write the equation for ammonia, you will have hydroxide in there, and the hydroxide will be on your ice table. So that's where I'm going to start. I'm going to take the pH, get the POH, find the OH of equilibrium from there, and then plug it into my ice table because it's a base. So first things first, let's go to the next page. I'll write it out. Hopefully you guys got the question down. We're looking for a concentration of ammonia that has a pH of 11.3, okay? So ammonia equation is a base because it's a Kb. So base plus water is going to go to NH4 plus OH. So Kb, it was given as 1.8 times 10 to the minus 5. That equals to NH4, OH, and NH3. And that's at equilibrium, okay? So let's go ahead and set up the, I can do the pH first. So pH was 11.3. So POH was 14 minus 11.3, right? So I get 2.7. So OH at equilibrium, which will give me the one of the n values of my ice table. I'm not having to solve for x here because I'll have this one as my x change. So I'm going to look for OH at equilibrium here, which is just take the POH here, 10 to the power negative POH, okay? So that will give me the molarity of, it's really 2, but I'll write it out. 1.995, 10 to the minus 3 molarity. So this is OH at equilibrium. It's like 2 times 10 to the minus 3. I'm going to put this in my ice table, but where does it go? So on my ice table, I have ammonia, I have ammonium, and I have hydroxide. Okay. In this case here, I don't know what my initial is, but that's what I'm looking for. So I guess I'll put this as unknown M, my molarity I'm looking for. I know I have 0 and 0, and then I have plus, plus, and minus. Remember that? And plus, plus, minus, and hydroxide at equilibrium is 1.995 times 10 to the minus 3. It's really just 2. But anyway, I'm just going to write it here. So this is basically 1.995 times 10 to the minus 3. Same number here, 1.995, 10 to the minus 3. And then the molarity here is M minus 1.995 times 10 to the minus 3. Right? So this number is really small because the K is small here. I'm just going to go ahead and assume it's like pretty much still M after you minus a small number. Okay, so I'm going to do that, and I can always check later, but it's really so small compared to that because the Kb is a small, small value. So in this case here, I'm going to plug in 1.8 times 10 to the minus 5 equals to these two, x and x, right? My 1.995 times 10 to the minus 3, and that one's squared because it's twice, divided by m, and I can solve for m here. It's 1.995 times 10 to the minus 3 squared over 1.8 times 10 to the minus 5, and I get like 0.22 molarity. That's just a unit, but the answer is 0.22, okay? So you can always check to make sure it's less than 5%. So 1.995 times 10 to the minus 3 divided by 0.22 times 100. It is less than 5%, it's 0.9%. Okay, so that's how you would solve for that question there. Let's go to the next question. We're going to do number 18 here. Says here, what is the pH of the solution prepared by mixing certain amount of something and something? So I'm going to go ahead and write it out. $40 mils of 0.1 molarity CH3CO2H with 40 mils of 0.01 CH3CO2Na. Assume the volume of solutions are additive, just basically they add up together simply, and that Ka is 1.8 times 10 to the minus 5 for CH3CO2H. Okay, so what you want to do here is you have to recognize this is actually a buffer solution because that's the ion and that's the ion. See that? And this one has H and this one has Na. So this is the conjugate, salt of the conjugate base. This is my acid here. So you'll have actually 10 times amount of acid compared to your base, right? Because it's like 40 mils of 0.1 and 40 mils of 0.01. So your base and acid are going to be 10 times apart. But we can always calculate that because you need that value there. Well, if the volume is the same, you can just use the molarity, but you can calculate the moles. I'll show you how to calculate the moles, okay? So in this case here, and if you wanted to save time, you don't have to calculate it. If you know it's 10 times difference, just say this one is 0.1, this one is 0.01 because the volume is the same. That's still the ratio of base and acid. So base is this one, acid is that one, okay? If you feel like, you're not really sure where I got that number from, I'm going to show you, okay? So in this case here, you can find moles of base, which is this guy, is 40 mils. And 1 liter is 1,000 mils, and then you do the molarity 0.01 moles, 1 liter. So you get the moles here is 4 times 10 to the minus 4 moles. And then you can do the moles of the acid, but based on looking at the volume and molarity, I can tell it's 10 times the difference, but I'm going to write it out anyway. 0.1. So this is 4 10 to the minus 3. So this is base, and this is my acid, okay? So I'll write down this part is base, this part is acid, okay? And then all you do is, because it's a buffer, pH equals to pKa plus log of base over acid. So if you didn't want to, you don't even have to do this. You can just do 0.01 for the base and 0.1 for the acid right here. But since I calculated moles, I can put that in, okay? pKa is minus log of Ka, that's given. And then plus log of base over acid. The idea is whatever the number you put in, either 0.01 over 0.1 or these two mole values, you still get log of 0.1 here. The ratio is still the same, okay? You can do it with these numbers and you see it's still this answer. Oh, 1.8, sorry. So your answer will end up being 4.74 plus log of 0.1, which is minus 1 there. So it's 3.74. Okay? Now, if they had the flip question where they had 10 times the base, then acid, and this is log 10 here, the answer would just be like plus 1 instead. Kind of like what you guys did in lab, okay? But just keep in mind that can change, but as long as you know how to put the ratio of base and acid in, you should be good and use the equation. So we have done this equation so many times, so I don't put this equation on your test, but you guys should remember pH equals pKa plus log base over acid, okay? All right, let's do the next question here. Everyone good with writing? What if instead of adding a strong base, a strong acid is added? Hold on a second, let me turn back. So this one's good here, right? I'm gonna go back to, someone had a question about adding strong acid here. If you had a buffer and you added strong acid, the equation changes, okay? The equation would be where, I'll show you. Right here. So this was the adding base, right? And if you added acid, you would use this equation. So calculate how much strong acid is coming in, calculate the moles of your buffer component in here, and you do the same table, okay? The table will have before, addition, and after, and your before will be just this and this, and then addition, and then after, basically, your base will go down by the amount of H plus that comes in, and your acid will go up by the amount of acid that comes in. So the base and acid ratio changes a little bit then as well. But the only difference is this was the equation when you add base, and if you add acid, you'll have this equation here. And then in this case, base will subtract the incoming H. This acid will add the incoming H amount, and then you put the acid and base ratio back into your formula. So that was a good question. So in this case here, so what happens is the equation here changes. You'll have, basically it flips around. And then the thing that reacts with the incoming H plus, which is the basic component, will go down, and the acidic component will go up in that case. And then you put the ratios back in here as well. Okay? You don't need to change the formula. It never changes. pH equals to pKa plus log base over acid. It will always work. Okay? No need to change it ever. Okay. So that was that part. Now let's go to another question here. We're going a lot slower because I'm writing each question now and we're doing different examples, but this basically we're trying to learn the material here. So I'm taking as much time as we need, okay? All right, let's do number 19. 2SO2 plus O2 goes to 2SO3. And it says this reaction is exothermic. What change will shift the equilibrium to the left? So which way is it going to shift left? What changes, okay? So A, decrease pressure. B, increase volume. C, raising temp. D, all of the above. E, none of the above. So in this case here, it says it's exothermic. So if it's exothermic, where is your heat going to be? In a reactant site or in a product site? So exothermic heat is coming out, exiting. Always remember the heat is on the product side, okay? So I like to write it in there, and then, you know, that way I can easily tell whenever we talk about raising temp. We can do that one first. When we raise the temp, you're raising heat, which is on the product side. It's going to shift the reaction to the left, correct? So raising temp is correct. It shifts it to the left. Decrease pressure and increase volume is literally the same thing. So if you increase the volume, it has more space. It will go to the space where we have more gas. This has 3 moles of gas. This has 2 moles of gas. So if you increase the volume, it will shift to the left because it will go to the side with 3 moles of gas, which is to the left. That's the same thing as decreasing the pressure. So the answer is actually all of the above. So when you read questions like this, don't get too excited and pick just the first answer you see, because it might be the other two if you see there's an all of the above or none of the above choice. Okay? So very good. So now we have number 19 done. So basically this question shows us that you need to know shifting right, shifting left, and the different scenarios that you they can ask you a question on this, okay? Number 20 is here's the question. You wish to prepare a buffer HC2H3O2 buffer with pH of 5.14 if the pKa is 4.74. What ratio of C2H3O2 negative to HC2H3O2 must you use? So it's just looking for the ratio of the base and acid in this case. So you have to remember pH equals to pKa plus log of base over acid. Don't use another equation, just you stick to this one. I know if you Google it, they'll give you different kinds, but that's why you don't Google stuff. Well, ask me or check with me. But we're gonna stick with this one in our class, okay? So when you have this here, pH, pKa, log base over acid, and you're looking for this. So you don't have to, you just have to solve for this number, log of what? So put in your pH. So pH is 5.14. Put in your pKa. pKa is 4.74 plus log of base over acid that you're trying to look for. So that goes there. 5.14 minus 4.74, okay? That equals to log of base and acid. So this one is 0.4 equals to log of base over acid. Now in this case here, we gotta get rid of the log by taking 10 to the power. So a biggest common mistake is when people take 10 to the power, they always like to stick a negative here when there's no negative. Please don't do that, okay? Just because a formula somewhere else showed you that you should do that, you don't do it here because this number is actually positive. Don't be changing it to negative. You will get the wrong answer. So just make sure you take 10 to the power on both sides. So 10 to the power 0.4 equals to the answer that you're looking for. So base over acid ratio is 10 to the power 0.4, and you get the answer is 2.51. So that means your ratio of base to acid is 2.51 to 1, basically. So the answer is 2.51. Okay, so that would be your answer for number 20 in this case. Just solving for that. So common mistake is people like to put a negative there if the number is still positive. So don't do that. Sometimes the answer here will be negative, then yes, you'll put a 10 to the power negative something. But if this number here is positive, don't change it to negative. All right, let's keep moving. Let's try some more problems. Let's do number 21. Number 21, calculate pH of 1.60 molarity KBRO. Solution. And then Ka for hypobromous acid, which is HBRO, is 2.0 times 10 to the minus 9. Assume KBRO salt completely dissociates. So this question here is actually a salt, because it talks about salt, right? It's a salt solution, but the K here is a spectator ion, and you're really looking at this guy. And if they give you HBRO, the SKA, the BRO hyperbromide here, it came from this acid. So that means this guy, BRO negative, is actually basic. So it's a basic anion here, and we'll write a basic equation. And when you have a basic equation, you will need to find Kb for this guy, which you can calculate from the Ka that's given for the acid version, okay? So I'm gonna go ahead and write the equation for the base plus water goes to base is adding a proton, so HBRO plus OH minus. We gotta remember, if you're writing a basic equation, you should end up with hydroxide ion there. That's one way to tell. So KBRO, KB for KBRO here is going to be HBRO times OH divided by BRO negative. Okay, so we'll have to look for what this KB is. How can you find that? Remember, Ka times Kb equals to Kw. Okay, so Ka for the acid, so Ka for the HBRO times Kb of BRO negative gives you Kw. So 2.0 times 10 to the minus 9 times Kb equals to, we'll assume it's still 25 degrees. So Kb is 1.0 times 10 to the minus 14 divided by 2.0 times 10 to the minus 9. That should give me a KB value. Let's see what the KB is. 5.0 times 10 to the minus 6. So I'm going to put this equals to 5.0 times 10 to the minus 6. And then I'm going to go ahead and set up the ice table for this guy here, okay? This equation basically. So I'm going to go to the next page because I don't have enough space here. Everyone good so far? All right, from my equation, I'm not going to put water in, so I have BRO in my ice table. I have HBRO in my ice table, and I have OH in my ice table. Initially, they said you have 1.6 molarity of KBRO, right? So I have 1.6 of this ion here. Because KBRO completely dissociates, and 1.6 of this ion will be there, molarity. So this is 0, and that's 0. And then this will go plus x, minus x, because it's 1 to 1. 1.6 minus x, x, and x. And then we're going to put it back into the KB formula. KB was HBRO, OH, BRO. So we'll put that in, okay? So x times x over 1.6 minus x. And we're going to go ahead and use the shortcut. Cross this one out, cross this one out. So x squared equals to 5.0 times 10 to the minus 6 times 1.6. That should equal to 8.0 times 10 to the minus 6. Take a square root of that. You get 2.83, 10 to the minus 3. And then that here is your x. And we can check it real quick if you want, but I can tell it's really small. (0.177%), so we're okay here. Okay, take this 2.83 as your OH, so POH equals to minus log of 2.83 times 10 to the minus 3. That would give me 2.55, and then pH would be 14 minus that. So sometimes people just memorizing this step here without setting the ice table, and you forget that your x is not always it's not protons, and a lot of people will choose 2.55 as your answer. Don't fall for that. Just remember 2.55 is actually POH. Yeah, you can use the shortcut on most of the exam questions. Guaranteed. Like, I would say most of them, because I don't like to pick the ones that you can't use shortcut, because that takes forever. Okay, so you can always assume you can use the shortcut unless the number is like you see how this k is like super small. Like when the k is small like this, you're good. And then when your k is like a big number, that's when you don't want to do it. Okay? Like when it's not negative 10 to the power negative something, then you don't want to use it. So that's a good question. So keep that in mind. We will always use shortcut in our test here. I'm not going to put the long hard ones on there. Okay. So we were done with 21. Let's go to 22. I hope this is helpful. I promise you the test it should be easier than a practice exam. Okay. I think, yeah, I put less of the harder stuff on the test. Like I think the practice exam is a little harder than the real test. So you should be happier like when you take your test. So do your practice exam. If you can get through the practice exam, you're gonna do great on the test. Okay. The periodic table will be on the top of every page of your test. So it will be like on the top of your test, like, you know, the last exam you have that too. You should have the periodic table, the constants, and whatever equations. Only the long equations are on there. You should see all of that available on every page of your test on the top. So you just scroll up if you need to look at the periodic table, okay? Especially, I guess the judging of your acid trends, you know, strength and electronegativity, you will need a periodic table, so scroll up. Other than that, I try to put the molar masses in if you need it. Ka values are always given, so you should be okay. Most of the time, you don't need to look at the periodic table stuff. All right, let's go to this question here. It says determine the molar solubility of CuCl in a solution containing 0.050 molarity NaCl. Ksp of CuCl is 1.0 times 10 to the minus 6. So this one here is not in water. This one here is in NaCl. So this is the one where it's not 0, 0 in your ice table, okay? So they give you the Ksp here. You know your solid is CuCl, and it's going to go to copper 1 and chloride, okay? So Ksp is Cu times Cl. And then when we go our ice table, you have Cu, Cl, it's ICE. So it's not 0, 0. You have 0.05 of your NaCl, which means you have some Cl in there in the beginning. So this one is 0.050. This one's still 0. Okay? And then we'll do plus S. So this is S 0.05 plus S. And then of course we're gonna do our shortcut again, right? So Ksp equals to S times 0.05 plus S. And then that one you can actually go ahead and cross out. Okay, now our Ksp was given as 1.0 times 10 to the minus 6, so let's put that in. And then we will solve for S. 1.0 times 10 to the minus 6 divided by 0.05. You get 2.0 times 10 to the minus 5. And we can always check it, but I don't think you'll have to check, really. I'd like to write out a check step for you, but you can tell that you won't have to check over here. And our test is always using the shortcut anyway. So 2.0 times 10 to the minus 5 divided by 0.05 times 100, and it's 0.04%. So we're good. So our S here is given as 2 10 to the minus 5. So that would be our answer right there, because they asked for the S molar solubility. Okay? Yes, you put the Cl there because it's a common ion. And this time we actually have CuCl, so it's 1 and 1 here. And because it was not in pure water, so if it was in pure water, this would have been 0 and 0. The only reason why this Cl is this number is because it had a common ion in a solution containing 0.050 molarity NaCl. And this gives me, in this solution here, I know I have 0.050 Na, and I have 0.050 Cl. But Na is just a spectator ion, so I take this value and put it in my ice table right there. Okay? Because it's a common ion now. If it was in pure water, this would have been 0, 0 because there's no ions in there. All right, let's go to the next question. Next question is kind of like some statements in there. So I'm going to go ahead and write it up. So it says here a solution containing CaCl2 mixed with a solution of Li2C2O4 to form a solution that is 3.5 times 10 to the minus 4 molarity in calcium ion and 2.33 times 10 to the minus 4 M in oxalate ion, which is C2O4 minus. What will happen once the solutions are mixed? Ksp of CaC2O4 equals to 2.3 times 10 to the minus 9. So this questionnaire is saying comparing Q to Ksp. If the Q is big enough, bigger than this, it will precipitate, okay? So I'll write all the answer choices that they'll give you. It says nothing will happen. Ksp is bigger than Q for all possible precipitates. B, a precipitate will form as calcium oxalate is not soluble to any extent. That's not true. Calcium oxalate is soluble, just a very, very little extent because they gave us the Ksp here. So B is like for sure wrong, okay? Nothing will happen since both calcium chloride and lithium oxalate are soluble compounds. And then D, precipitate will form since Q is bigger than Ksp for calcium oxalate. Now there's an answer choice for E. It says not enough info. That one's just really a distraction, okay? We have enough information. So don't pick E. Don't pick B either because I gave you the Ksp, you know it's somewhat soluble. Very, very small, tiny amounts. So all you do is you take your Q values. Okay, this is 1 Ca times C2O4. So I'm going to work my work up here in a different color. That way you can see it. Right here. C2O4 solid, it's gonna break apart into Ca2 plus and C2O4 2 negative. So your Ksp is Ca times C2O4 2 negative. So your Q is basically molarity calcium times molarity oxalate, which is this and that multiplied together, okay? When you multiply this and that together, so I'll write down the Q. The Q is 3.5 times 10 to the minus 4 times 2.33 times 10 to the minus 4. That equals to 8.0 2 10 to the minus 8. And that's bigger than your K. See how Q is bigger than KSP? Because this is 10 to the minus 9, this is 10 to the minus 8. So my answer is going to be D here. Okay? Everyone still follow? All right. Let's keep moving to number 24. So number 24 is something
Sorry,
we
answer for 23.
well, you still need to take a look at it for a little bit more. Number 24, there's no math. 25, there's really no math either. Maybe I'll just show you guys the question, okay?
Thank you.
All right, you guys done with 23? So I'm going to show you number 24 here. Says here, what is the conjugate acid of H2PO4 negative? If they ask for a conjugate acid, you want to write this guy as a base, okay? So if this was a base, H2PO4 negative is a base, you want to add a proton, right? When you add a proton, you get H3PO4. So that would be the conjugate acid. They can easily change this answer and ask you conjugate base here, because this guy can go both ways. If it was conjugate base, this guy would have behaved as an acid, and your answer would have changed to A here. So just keep that in mind, okay? So if they ask for conjugate acid, it behaved as a base. If they ask for conjugate base, it behaved as an acid. All right, so the next question, number 25. I'll leave this so you can copy the answer choices. It says, which one is Kp equals to Kc? You have to make sure delta N is equal to 0 for Kp, so Kc, and you never count solids or liquids. So don't count solids or liquids. Okay? So this one is 2 minus 1, so that's 1. This one is 4, 10 minus 9, so that's 1. This one is 1 minus 3, so negative 2. This one is 2 minus 2, so that's 0. This last one is 2 minus 4 is negative 2. So the only answer that has 0 here is D. So sometimes you'll see your answer choices have solids or liquids in them. Remember, don't count solids or liquids, and you want to make sure moles or products minus moles or reactants is 0 to get Kc equals to Kp. Everyone good with this? I'll give you some time if you wanted to write it down, okay? Can I move to the next page? Are you guys all right? Yeah, I'll give you some time. Let me know when you're done, okay? We only have a few questions left. We are taking our time, and I do want to explain things in detail. So this one's an easy version of it. You know, there will be some versions where you have solids and liquids thrown in. Just remember not to count the solids or liquids, okay? All right, I'm gonna go to the next question. Now the next question has an image on it, so I will show you the image, okay? Don't look at the answer. Or you just saw it, but never mind. So it says here, what is the pKa of the behavior of titration solution that's in a flask? This question here is asking you what the pKa is. Remember, this is the pH equivalence point. Halfway to equivalence point is like, if this is 90 or 100, and then this is 50 right there. So that would be my pKa, okay? How do I know that? And then once you know pKa, 14 minus pKa, you get pKb. That's why the answer is 9 and 5. I wanted to show you where you see that from in our notes. See the same graphic? Exact same picture, right? See how this is a equivalence point, and right there is where you find your pKa. Okay, and then if this was pKa of 9.24, then your pKb would have been 14 minus 9.24. So just remember, if you see a picture like that, where do you find a pKa? It's always half of equivalence point. Doesn't matter if it's acid or base that you're titrating. Like in this case here. So I'm going to show you another picture from our slides here. So this was 25 here, that's equivalence point. Around 12 and a half here, right there. So when you get pH equals to pKa. Same idea, okay? Always the half equivalence point, you get pKa. Everyone good? Okay, the next question, I will write it out, okay? Everyone all right with this? So just remember to draw the picture out and just know that this does come straight from our class notes, okay? All right, I'm gonna write question number 27. Calculate pH of a solution that is 0.322 molarity nitrous acid, which is HNO2, and 0.178 molarity in potassium nitrite, KNO2. The acid dissociation constant, dissociation, I spelled it wrong. Of nitrous acid is 4.50 times 10 to the minus 4. Assume Ka is very small compared to initial concentrations. So I want to explain what this statement means. This statement means use a shortcut. Now, this statement means use a shortcut, and it also applies if you have a buffer. That means use the equation, don't use the ice table. Just go straight to the equation. Do you see this as a buffer? The acid and the salt of the conjugate base. So all they want you to do is find the pH of this buffer. They just worded it like long with like, you know, they call it an acid dissociation constant instead of the Ka. So, you know, you want to make sure you know what Ka means is the dissociation constant, equilibrium constant of nitrous acid. And that's Ka. Okay, so our formula is going to be the same. pH equals to pKa plus log of base over acid. Okay, so the pKa is given, it's right there, was minus log of that. And then plus log of base over acid. So what's my concentration of base? 0.178. What's my concentration of acid? 0.322. So this one is the one that's easy. You don't have to calculate the new molarity. It's already giving you what the actual concentration is. There are questions that you will have to calculate the molarity, okay? So just keep that in mind. You'll get your answer here. This is going to give you the answer of 3.09. Now, let's do the next question. It's a word problem, so I'm going to write it out. A solution is prepared by dissolving 0.25 moles of formic acid and 0.23 moles of sodium formate in water sufficient to yield 1.00 liters of solution. And they're saying that we made a buffer of 0.25 acid, 0.23 base, and 1 liter, okay? And then it says the addition of 0.05 moles of NaOH to this buffer solution causes the pH to increase slightly. In fact, we know how to calculate that, right? They're not asking you to calculate though. They said the pH does not increase drastically because NaOH reacts with the blank, whatever does NaOH react with, present in the buffer solution. The Ka of formic acid is 1.8 times 10 to the minus 4. So what is it reacting with? Formate BH3O plus formic acid DH2O E. This is a buffer. pH does not change upon addition of acid or base. All right, I didn't realize you couldn't see. But so there's that question there. Now there's a lot of varieties of this question that it can ask you. Sometimes they'll give you the buffer here, and sometimes they'll add acid. If you add acid, acid reacts with the weak base component of your buffer. So acid, if you add HCl, HCl would have reacted with a weak base, which is this guy, formate here. But in this case, we're adding strong base. Strong base is going to react with the acidic component of your buffer, which is going to be formic acid. So these guys here are just distractions. And this statement E is actually not true. pH does change very slightly. It just, depending on how good your buffer is, that's how much it can resist the pH change. So if you add an acid, it will react with the conjugate, with weak base component, which would have been this. But since we're adding sodium hydroxide, it was actually reacting with formic acid. So I want you guys to be able to tell who's reacting with what, okay? All right, let's do question number 29. Everyone good with this? I'm gonna go ahead and, actually, I might not have enough space down here, so I'm gonna change the page. Are you guys good with this? Let me know. And you don't have to write all of this, just know that if it's base, it reacts with the acid component of your buffer. All right, I'm gonna change the page. Now, if you need me to come back to it, I will do that for you, okay? Let's go to number 29. We're almost done. Your test only has 20 questions, okay? 20 and 2 bonus. And it will be the easier, hopefully less math versions. Let's see, consider the following reaction. So our reaction here is CH4 plus 2H2S goes to CS2 plus 4H2 gas. All right, and then it says here, any reaction mixture initially contains What does it contain? It says initially you have 0.50 molarity of CH4 and 0.75 molarity of H2S. If the equilibrium concentration of H2 is 0.44, find equilibrium concentration equilibrium constant, never mind. We're looking for equilibrium constant, which is the K, okay? The reaction. So this question here is where instead of putting X, you know the change of one, you back calculate the change of the others. So our K here is going to be CS2 times H2 to the power 4, CH4, and then H2S to the power of 2. Okay, so that's what you will get, and you're trying to look for the answer here. Let's set up our ice table. Okay, ICE, so initially I have 0.5, 0.7500, and it says equilibrium concentration is 0.44. This is plus 4x. This is minus x plus x, not minus, because this side is plus. So this side will be minus 2x minus x. And what is x here? X is 0.11 because 4x is 0.44. Okay, so this answer will be 0.11, 0.75 minus 2 times 0.11 equals 2, and then 0.5 minus 0.11 equals 2. This one is 0.39. This one here is 0.53. And then you just put these values up in this equation. So CS2 would be 0.11, H2 0.44 to the power of 4, and then 0.39 times 0.53 squared. And you should get your answer for K as 0.0376. Okay, so that's how we do that question there. So this one is basically they give you what the X is and you just back calculate the others, which is what you did in lab a long time ago. All right, I'm gonna write the next question, which is our last one. What is the KW of pure water at 50 degrees if pH is 6.630? So they're asking for pure water, and pure water, you know that H and OH is the same. Okay? So if you know the pH is that, pH is 6.63, H plus is going to be 10 to the power negative 6.63. So let's see what the answer is. H plus here is going to be 2.34 times 10 to the minus 7 molarity. And if you know H and OH is the same, that means H plus and OH both are the same molarity of 2.34 times 10 to the minus 7 molarity. And how do you get KW? Is H times OH, which means it's 2.34 times 10 to the minus 7 squared, because it's this and this times together. So you should get your answer of 5.50 times 10 to the minus 14.